morning. This is Unlock Circuits 18EC42, Module 2, MOSFET Amplifier. Configurations will taking up some of the exercises corresponding to the MOSFET Amplifier configurations. For this, we'll be using the document which corresponds to this, wherein 5.6 is the basic MOSFET Amplifier configuration, which is same thing as the MOSFET Amplifier configurations. Now let us take some of the examples there. So 5.26, show that AV is equal to minus GM multiplied by RL in parallel with RD in parallel with R0 for the common source amplifier, wherein small R0 is the output resistance of the MOSFET, RD is the drain resistance, and RL is the load resistance. The circuit for the common source amplifier, considering the RD as well as RL, is written something like this, or it can be considered like this, wherein we connected here VCC. So in the analysis, VCC goes to the ground, so that means to say that RD and RL will come in parallel, and that is same thing as this. So either one can write this circuit or this circuit, both refer to the same thing. Now, if we replace this MOSFET over here by means of the equivalent circuit, which is GM-VGS in parallel with R0, this is the equivalent circuit on the output side, and on the input side, we don't have anything here because the input impedance of the MOSFET is infinite. So it's open over here. So this is RSIG, this is VSIG, this is VGS equal to VI, this is GM-VGS, R0, RD, and RL. So equivalent circuit of the MOSFET is this part. Now this further reduces to the output side, particularly GM-VGS and R0 in parallel with RD in parallel with RL, and the voltage is taken across this combination over here of the current source as well as the resistance. So this current over here, you can see that it is downward here. That means the current should be flowing like this. From this point, the current will be flowing like this. So it's flowing upward as far as the resistance combination of R0, RD, and RL is concerned, and hence V0 will be equal to minus GM-VGS multiplied by R0 in parallel with RD in parallel with RL. If it's flowing downwards here, then it would have been plus, but it's flowing like this in the resistance, therefore it is minus. So taking the VGS on the other side, AV is nothing but V0 by VGS, that is equal to V0 by VI, because VGS itself is VI. If you see over here, VGS is equal to VI, and hence we write here V0 by VI is equal to V0 by VGS is equal to minus GM R0 in parallel with RD in parallel with RL. So this is the expression one can write for AV, considering RD, RL, and R0. Where R0 is the internal output resistance of the MOSFET. Now let us take the second example of 5.27, the CS amplifier here, that is common, we are considering a common source amplifier with ID equal to 0.25, VOV equal to again 0.25 volts here it is milliamperes, RD is 20 kilo ohms, VA, the early voltage is 50 volts, RC is 100 kilo ohms, and the 20 kilo ohms is the load. We need to find out the RN, AV0, that is the open circuit voltage amplification, R0, the overall output impedance of the what we call circuit, RN is the input impedance, AV is the amplifier amplification or gain proper, and this is the overall voltage gain considering the source also into consideration. So if to maintain reasonable linearity, the peak of the input signal is limited to 10% of the T to 2 VOV. 2 VOV is 2 into 0.25, that is 0.5, and 10% of that will be 0.05. So if that is the input sine wave signal, then the peak of the input sine wave signal is 0.05 volts. What is the peak of the sine wave voltage at the output? So input peak wave is 0.05, then what will be the output, what you call sine wave voltage at the output. So the answers are given over here, and we need to find this value of itself for values which are nearer to that. So given ID is equal to 0.25, VOV is equal to 0.25 again, RD equal to 20 kilo ohm, VA equal to 50, RC equal to 100, load RL is equal to 20 kilo ohm. We need to find these quantities over here. Then if VI is equal to 10% of this, what is V naught? So Ri is basically infinity. Ri is the input impedance of the MOSFET, and that itself turns out to be infinite over here, because you can see in the circuit it's open. In the LS circuit, if you see over here, it is open. So therefore, Ri looking here will be equal to infinity. Then R0 is equal to mod of VA by ID. VA is 50, ID is 0.25, so therefore this will be 200 kilo ohms. The capital R0 will be small R0 in parallel with RD, that is equal to 200 kilo ohms in parallel with 20 kilo ohms, and that will turn out to be 18.18 kilo ohms. And that is the 200 into 20 divided by 200 plus 20. Then AV naught will be minus GM multiplied by R0 in parallel with RD. Please remember that when we write AV naught, it is the open circuit voltage amplification, wherein RL is considered equal to infinity. So RL is considered equal to infinity just means that we need to consider only this R0, not R0 plus RD in parallel with RL. If you consider that, then naturally it will not be AV naught, it will be AV. So this will be value. We don't know GM, so we need to find out GM. So GM is equal to 2 IDB VOV is the formula for that. 2 into 0.25 A divided by 0.25 V. So this and this will cancel, and we are left with 2 milliamperes per volt. So AV naught is minus of 2 milliampere per volt multiplied by 18.18 volts. So that will give us the value. This is 18.18 kilo ohms. So if you multiply that, kilo and milli will cancel, and we'll get 36.36 with a minus sign as the open circuit voltage gain. AV is the one which is by considering the RL also, so wherein we can write this minus 2 milliampere per volt as GM, and R0 and in parallel with RD we already found. RL is what we need to write 20 kilo ohms, and then we'll get minus 19 volts approximately. Might not be exact, but approximately. So GV will be equal to AV equal to minus 19 volts per volt, because the value of Rn is infinite. Both the GV and AV will be same. When VI is 10% of the T2 VOV, as I told, 10 is by divided by 100, that is 10% multiplied by 2 into 0.25 will give you 0.05 as the VI. If this is the peak value, then what is the peak value at the output? So that will be AV into VI minus 19 into 0.05, and that will be minus 0.95. So peak is 0.95. Next, we will consider the 5.28. So in the earlier exercise, we applied an input voltage of VC equal to 50 millivolts peak and obtained an output signal of 1 volt peak. Assume that for some reason we now have an input signal VC equal to 0.2 volts peak, and that we wish to modify the circuit to keep VGS unchanged. So we are modifying the circuits to keep this VGS unchanged, and thus keep the nonlinear distortion from increasing. What is the value we should use for RS? So now what we are using is the common source amplifier with source resistance, because we are using RS. What value of GV will result? What will be the peak signal at the output become? Assume R0 equal to infinity. So now for the VC of 50 millivolts, we had V0 is equal to 1 volt for CS amplifier without RS. Now VC is equal to 0.2 volts for CS with the RS. with the VGS unchanged, and naturally when VGS is unchanged, we see that the V naught also remains unchanged, only we are trying to increase the VSIC from 50 millivolts to 0.25 millivolts, but equivalently we are introducing RS over here, whereas RS was not there at this place. So to keep the nonlinear distortion from increasing, what is the value of RS and what is the value of GV and what is the V naught peak. So GV without RS is minus 1 volt by 50 millivolts. So this is 1 volt by 50 millivolts, that is equal to 20. GV with RS is minus 1 volt by zero point 0.2 volts is equal to minus 5. The reason why we are considering here minus is the common source amplifier, uh, whether it is with or without RS, will always give a negative value of GV. So 1 plus GMRS, that is the feedback factor, by considering the source resistance, that turns out to be 20 by 5 equal to 4. So GMRS will be equal to 3, RS will be equal to 3 by GM is equal to 3 by 2 milliampere per volt, which was calculated in the earlier problem 5.27. So therefore we have here 1.5 kilo ohm, which is again given in the answer over here. So if VGS is unchanged, then V naught will also be unchanged, and hence we'll have 1 volt, and the same is being specified over here. This is minus 5, and that is already mentioned over here. So with this, we'll come to the end of the what we call first part of the exercise, and